So what we want to do here is that we want to do 2 examples, and then we want to go into the last thing that we want to talk about, which is Compton scattering. Compton scattering is something that happened way after the photoelectric effect, but it makes sense to talk about it right now because it's sort of like in line with the photoelectric effect, that there's no way that the classical model of light being a wave, it can explain. So what I want to do now, excuse me, is that I want to go in and I want to share my OneNote and try to catch you up as quickly as possible. And we were on example 3.1. Okay. So in example 3.1, what we saw here is that we did the following thing. We ended up looking at this example where we have light of 200 nanometers shines on an aluminum surface of 4, and it has a binding energy or a work function of 4.2 electron volts. In other words, this tells us about the depth of the well and is required to eject electrons. So what is the kinetic energy of the fastest and the slowest ejected electrons? And then what is the stopping potential for this situation? What is the cutoff wavelength for aluminum? And the picture that I've been trying to stress here is that we look at a well. And when I look at a potential well, what you're seeing here is that this potential well is telling us that if I shoot in some photon, where its energy is described by HF, that the slowest possible ejected electron is one where the kinetic energy is 0. But this electron will never exist. And the reason why it won't exist here is that because the atom is now more positively charged. And because it becomes more positively charged, it attracts that electron right back into there. So this is what they call the cutoff. Okay, so sometimes you'll hear that this is sort of like the cutoff, or sometimes you hear the threshold point. But in reality, that electron will never occur because it just gets reabsorbed right away. So this would give you the slowest possible situation. Now, when do you get K max? Well, why a max? Right? Why is this maximum kinetic energy? What you find here is that you have a layer at the very top of the, or the layer of the metal skin, if I could say that. It's actually called the skin depth. If you've taken 4B, you may have talked about the skin depth. And the skin depth is typically where the electrons kind of live. And so this is essentially what this is right here. And these electrons are all roughly right into that region. So because they're at the highest part of the well, what you'll find here is that these electrons when ejected do not collide with other electrons. On their way out. And because of that, you're going to get K max. You're going to get K max. On the other hand, you could think about the following thing. I send in a photon, and when you look at the atom, it's not this, one close to the surface that's being ejected, but you can eject ones that are further down. And if they're further down, what you're seeing here is that electrons deeper in the well Remember, when we say well, remember that that we're not talking about the inner electrons. We're talking about the surface electrons. That the electrons deeper in the well collide with other electrons. And as a consequence, they have less than Kmax. And because they have less than Kmax, we saw that when we were looking at the photoelectric effect, that what you end up getting here is that you get these electrons here. And what I mean by this thing here is that you could see that if I go share my screen with you, and you're looking at these, you could see that some are clearly traveling faster and some are clearly traveling slower. So the slower ones are the ones that are having to fight to get out because they're doing what? They're colliding with these other electrons right here, right? So you want to sort of like pay attention in that sense here. So now what we want to do here, oh shoot, hold on a second. I ended up just closing that applet, which I need for and one of the things that I want to show you. So I have to go back and open that. So here I go. So now what's going to happen here? So what happens here now is that, what do I mean by Kmax? So the maximum kinetic energy, right? So when I'm thinking about Kmax here, what I'm seeing here is that the maximum kinetic energy implies then that Kmax has to equal HF minus the work function. And if I want to calculate that value, we typically don't calculate frequency here. What we end up calculating is that we multiply and divide by C so that we're not doing anything. So then all of a sudden what I can do here is I could go in and put in my numbers here. So if I do this, then I'm going to get HC over lambda minus the work function. So if I calculate this thing, this is going to be what? 240 electron volts nanometer. The wavelength that they're giving us was 200 nanometers minus the work function, which is 4.2 electron volts. And if I compute this thing here, what you're going to find here is that I get a value of 2 volts. I get Kmax is 2 volts here. Or 2 electron volts. I should be careful here. But what we're really talking about, though, is that when you look at this thing, is that, remember, the stopping potential is related to Kmax. So in other words, if I look at Kmax, it's also a measure of V stop. So we never calculate E. So when I look at what is this stop voltage, you're going to find that this will then be 2 electron volts divided by E. And you could see that we don't calculate it because it cancels out. So then this tells us here that this is 2 volts for V stop. So there's 2 ways that I can look at that. I can look at it in terms of Kmax or V stop here. And again, what is this? This is the height of electrical ramp. It's a little bit more, but I think that's the important thing. So then the next thing that we're really looking for here in the question is that it's asking for, now that we talked about the fastest, we talked about the slowest, we're asking, what is the stopping potential for the situation? Now they're asking, what is the cutoff wavelength for aluminum? So let's go look at that. So when I plot this thing, let's go draw a picture of this to try to make this as clear as possible here. What you're seeing here is that here's my V-stop, okay? And what you're seeing here is that there's going to be a point here where I'm going to have where no electrons actually gets done. And so this guy right here is a so-called cutoff. What do I mean by a cutoff? That means, so if I was to sort of like give you a sense of what I'm talking about, this whole region essentially says what? No ejected electrons. So the cutoff frequency says that if I have any frequency less than the cutoff frequency, I'm going to get no electrons. On the other hand, I have this guy right here. If I have a frequency above this region, then I know here that I'm going to get ejected electrons. And since we're talking about aluminum, I should say that this curve is true for aluminum. So if I want to calculate what this cutoff wavelength or frequency is, it has to be at the point where V stop is 0. But wait a minute, V stop is proportional to the kinetic energy, maximum kinetic energy. So then this guy will then tell me what the cutoff frequency is. So the cutoff frequency is when K is equal to 0. So if that's the case here, then that means K, which is 0, then has to be this thing right here, where now this has to be the cutoff. So this implies if I go and I solve for H, this cutoff energy required, I can rewrite this in terms of what? The cutoff wavelength, using that relationship for waves, and this has to be equal to the work function. So when we were talking about the 0 kinetic energy point, right, we're really talking about this first point here, where it just gets out. And so you could see that from a bar diagram process, you could see that if I go in here and I just kind of highlight this guy, let me bring this down here just to show you what I mean. Picture-wise, it looks something like this here. That just essentially means what? That the energy of the photon right? This is the energy of the photon. That has to equal the energy of the well, but the well is negative. So you could see that this bar diagram, they're equal and opposite. So therefore, at this point here, you could see that K has to be equal to 0, just from a bar diagram. And so what this tells you then, this is the minimum energy that has to be this scenario right there. So picture-wise, that's what that means here. So now I want to go and solve for lambda cutoff. So if I solve for lambda cutoff here, from this equation right here, you could see that this guy then has to be what? HC over this. And then if I start putting in my values, I'm going to get 4.2 electron volts. And then in the end, it's going to be 295 nanometers. And that's the so-called cutoff wavelength. So again, what does this mean here? This means that for waves, lambda greater than lambda cutoff, remember, shorter waves have higher energy. Longer waves have less energy. So for waves where their wavelength is greater than the cutoff, this implies that no electrons are ejected. Whereas if lambda is less than the cutoff, then what you're going to find here is that electrons are always ejected. So what I wanted to do here is that I agree that we're just getting some numbers here. And what I'd like to do here is I'd like to go in and sort of like use the PhET applet. Now, in hindsight, now that I'm rewriting my notes, I shouldn't have used aluminum. I should have used sodium or one of the elements. Aluminum is not in the PhET applet. So what I want to do here is that I'm going to use for sodium. And the reason why I'm going to do this, because now we could use some numbers to actually show you what do I mean by that. So the first thing that we want to do is that I know that the binding energy / work function of sodium is this. So sodium has a work function of 2.28 electron volts. And what did I do? I just looked it up. Because of this, I could then go get the so-called cutoff wavelength. Of sodium. So if I go calculate the cutoff wavelength, it's the same thing as up here. So then this means here that lambda cutoff for sodium is then going to be, of course, H over this guy. And if I plug in my values, I'm going to get 240 electron volts nanometer divided by 2.28 electron volts. And if you compute this, you're going to see here that this is 544 nanometers. And that's the cutoff. So we have a value now that we can actually use here. So what I'm going to do here is that I want to shine light onto sodium. And what I'm going to do is I'm going to start off with, so I'm going to move over here. And what I'm going to do here is that I'm going to shine yellow light. And yellow light is going to be, yellow light is about 560 nanometers. And if I shine green light is about 530 nanometers. And so what you're seeing here is that if I shine yellow light, note that yellow light has a longer wavelength than the cutoff frequency. So if I shine yellow light onto sodium, this implies that I'm going to get what? Well, this tells me here is that yellow light, oh man, I got to take this guy off. So how about if I do this type of thing? So then yellow light is greater than the cutoff. So that means what? No electrons ejected. But if I shine green light, I could see here that green light is less than the cutoff. And if it's less than the cutoff, then that means electrons are ejected. So let's go to the Phys applet. So if I go and I do that, okay, are you seeing my applet here? You seeing the Phys applet right now?
Yeah.
Okay, so now let's go look at this thing here. So yellow light, so I'm gonna come in here. Yellow light is 560, around 560. Okay, come on, baby. There you go. So now look what I'm gonna do. I'm gonna increase the intensity full blast. And you can see nothing's coming off. Okay, I got full intensity. So now what I'm gonna do here is that I'm gonna shine green light, which is 530. So if I go to 530, I got green light, and you could see that I got electrons coming off. That's what that cutoff frequency means. That if I'm below that cutoff, I'm not going to get electrons. But if I'm above that cutoff with wavelength, I'm not going to get them. But if I'm less than that wavelength, then I'm going to eject them. That's what that cutoff frequency is. So now what I got to do here is that I got to come in and I got to go to the next example here.
What's all this about wavelength anyways? Aren't we talking about particles?
Oh, we're talking about, oh, there's always a smartass in the crowd. And so you're right. I am lying to you, right? When I'm, yeah, what's all this bullshit? I agree. Photons have no wavelength or frequency. And what's more appropriate to talk about is energy. In essence, when we associate color, right? When we associate with color, you know, color is a human perception, not the other way around. It's not nature. But that's a discussion for a whole other topic. And by the way, people don't like that conversation. I'll tell you that right now. As soon as we start to say, I say things like, oh yeah, you know, oops, sorry about that. Color. Oh man. God, man, it's an ugly conversation. I'll tell you that right now. People have a lot of emotions like, oh, it's such a nice, warm yellow color. And I go like, that's a human construct. It's not nature. People don't like that. Oh man, I used to try to do that in physics 4C and physics 10. Physics 10 is even worse. And they'll say, bullshit, color has meaning. And I'm going like, no, it doesn't. But that's another conversation for another day. But we could have that. When we can, the only way I'm gonna have that conversation is I probably shouldn't say this online, like over a beer or something, because that's a long conversation, not some simple conversation. I'll tell you that much right now. Okay, here we go, 3.2. So it says the work function for cesium is 1.9 eV. So again, that's just the depth of that. And it says find the threshold. So remember, threshold is also cutoff, frequency and wavelength. There's a very good reason why I said frequency and wavelength, because it requires two different types of calculations. And then it says, then find the stopping potential if the wavelength of the incident light is 300 and 400 nanometers, and then interpret the difference between these two. So the first thing that I would do here is that we're talking about what? The cutoff. So the cutoff slash threshold frequency and wavelength is when K is equal to 0. That implies that the energy of the photon must be equal. It has to be balanced out by the depth of the well. So what do I mean by that? Well, there's two pictures that we should have in our mind. Well, if I look at V stop, there's that one magical point right there. So if I look at that magical point, it means this. So I have something like this, and this is the region where I get no electrons. This is the region where I get electrons, right? So I get no ejected electrons, and then here I get electrons. In other words, that's the cutoff. And what do I mean by the cutoff? I mean this expression right here. And so if I draw this picture-wise, if I'm focusing on the cutoff, then I look at my well, and my well tells me that it looks like this. That I have some well here, and inside my well, I have a series of electrons. And I'm going to focus on one of these wells. And so now I'm sending in some little localized packets. And all I know is that the energy of these guys here are just balancing each other out. So when I get this electron out here, I know that K is equal to 0. It's a stationary electron. Now, what you find here is that to get the frequency, right? So there's two things here. I really wanted to focus on two things, frequency and wavelength, because it does require two different calculations here. And one of the things that I stated earlier here is that if you're going to calculate the frequency, you have to use the value of H. There's a good value and there's a bad value. So which one's the good value? So here we go. So to get the frequency directly, you have to use this value of H, which is 4.136 times 10 to the negative 15 electron volts times second. So when you use this, this is what you find here. I know that the threshold is when the energy of the photon has to be balanced out by the binding energy or the work function. So if I do that, you could see here that the cutoff, of course, is then going to be the work function divided by the H. So if I plug in my value here for cesium, you could see that cesium is 1.9 electron volts. This is 1.9 electron volts, and this is going to be divided by 4.136 times 10 to the negative 15 electron volts per second. And right away, you could see that the electron volts are going to cancel. So I now have units of 1/2. But if it's 1/2, that tells you that this guy has to be 4.59 times 10 to the 14 hertz. And if you find out that this is going to be the cutoff. Now, what you find here is that if you're anything like me, I have no idea what the hell that even means. So what do? I consult tables. And what you're seeing on this table right here is that you could see that if I have 4.59, times 10 to the 14 hertz, what you're going to see in this case here is that this guy is going to be where? Well, what you're going to see here is that implies that that this frequency looks like it's going to fall right into this region right here. So you could see that right here is that frequency. It's in between these two intervals here. So you're going to see here is that this guy, this is red light. Now note, looks like it's right at the boundary between red and orange. So that probably means that you're having a lighter red instead of a darker red. Darker red is going to be way over here, right at the edge of the spectrum here. And look what we already found here. Note that they're telling us about the photon energy right here. And so when you look at the photon energy, we already knew that the energy of the photon, which is of course the cutoff, had to be equal to this. So we already knew that this was the case. And look what it's doing. It's telling us that that is exactly what you're seeing, right? This is the minimum energy to eject an electron to. So you could see that it's making sense as far as what we're calculating. So what about the cutoff wavelength here? So the wavelength requires a different calculation, which we've already done here. To get lambda cut off, as we had just did here, we could then come in and just say, okay, that the energy of the photon, which is equal to hc over lambda, if this is the minimum energy, that also has to equal to the work function. And when you calculate this thing, you're going to find that this is hc like this. And then if I start to plug in my values, this requires the hc value that we've talked about there. And in this case here, we know that the work function is 1.2. Calculating these guys, we find out here that the value that I get here is 654 nanometers. And this is the cutoff. So again, what you're seeing here is that this value is falling in where? Right in between there. So the values of the table that you would get off the web, which is what I did when I got this guy here, is exactly what we would have expected here. So that's a good sign right now. So now what I want to go do is that I want to go do the rest here. So the question then asks what? It's asking, find the stopping. How about if we bring it down here? It's saying, find the stopping potential if the wavelength of the incident light is 300 and 400 nanometers. Now, granted, we know what this guy is, and we know the wavelengths, but we don't know what f-stop is here. So when I'm looking at this thing here, what you're going to find here is that if we want the stopping potentials, right, So I think this is question B, C. So let's look at what you're going to see here is that we already said here that Kmax had to be the same as the stopping voltage, and that this guy has to be what? The energy of the photon minus the work function. And so we could then go in and we can just compute both of these. So here I go. So what I'm going to look at here is I'm going to want, now it's common to, when I say stop voltage, should I have an E? Personally, I typically always leave the E there because I don't ever want you to plug in the value for E, ever. So a lot of the times what I do here is that if I say calculate the stop voltage, I'll just leave it as E stop. Now I could cancel out the E's, and maybe I should do that once so you can see what I'm talking about. But for 300 nanometers, then according to this guy here, it's got to be what? Well, it's got to be HC over lambda minus the work function. So in this case here, then it's got to be what? 1240 divided, in this case here, 300 minus the work function. And we know that the work function is this here. So it is true, oops, wrong one, that I do have E on both terms here. And if I compute that, then I'm going to get that this is going to equal to 2.23 volts here. Oops, my bad, electron volts. And so this becomes the stop voltage for 300 nanometers. Now, I know that I'm not using my language correctly because that's energy, that's not the stop voltage. But you can clearly see that I could come in here and I could cancel out the E's and just say, oh, what's the stop voltage? What would you set your power supply to? It would be 2.23 volts. And if I repeat the exact same calculation for 400 nanometers, the exact same thing, then I'm going to get that this is going to be 1240 divided into it by 400. And the value that I end up getting is 1.2 electron volts. And that's going to be my EV stop. So if I look at this guy here, and you could see that the longer wavelength is easier to stop because it has a value of 1.2, whereas the shorter one has a higher one. So what you're finding here is that I could then go in and say here, just as we expected here, is that shorter waves have higher energies, and therefore electrons have more kinetic energy. And remember, this is of course proportional to V stop. Whereas if I have longer waves, they have lower energies. But if they have lower energies, they have less kinetic energy and therefore V stop here. So I'm finding here that I can go in and actually sort of like looking at this thing, that interpreting these values. Okay, so I'm done with this here. I now want to go on and I want to talk about Compton scattering. And what I want to do here is that I want to sort of like explain what is going on here. Okay, I really want to explain what's happening. And what I'm going to do here is that I think I'm going to do a lot of talking right now, probably for the next 2 to 3 minutes. And I'm not going to write very much here. And the reason why is that I want you to have a physical understanding of what was going on so that you understand why we're having what we have. Okay. And so what I'm going to do here is I'm going to stop sharing my screen for a minute, and I'm going to now want to talk to you a little bit. I want to talk about Compton scattering. Now, what's special about Compton scattering? Well, I think we should summarize where we're up to now. After the photoelectric effect, how is one to interpret what light is? When one looks at how light interacts with matter, in this case, if we're talking about the photoelectric effect, people are seeing atoms for the first time. So if with the photoelectric effect, you're finally seeing an atom, what we can do here is that there's 2 ways to view this. So the first thing that I would say here is that in pre-1890 instruments, they did not have the capabilities of looking at atomic structure of materials. What do I mean by that? They just didn't have instruments that had a high enough energy. Therefore, the wave model of light, the way Maxwell wrote it down, and I want to remind you that Maxwell, when his electricity magnetism did not include atoms. Atoms did not exist at the time. So the wave model of light was able to explain quite well all experimental data. So what I say here, that is the pre-quantum mechanical era. That is that they had a macroscopic view of light when light was interacting with the material. They were not seeing the atomic structure. But then came the next stage, and starting around 1890, when they started building better and better electronic equipment, that technology allowed people to shine electromagnetic radiation. And what they were doing here is that they were getting below macroscopic and they were getting to microscopic. They were starting to see the atomic structure. And this is where the classical picture started to have problems. Of course it did. Beforehand, classical physics didn't see atoms. All of a sudden, they're seeing atoms for the first time, and their theories never had a chance. So now, as they're starting to look at light at this microscopic level, they're starting to see how light is interacting with atoms, and classical physics could not explain this microscopic interaction with light interacting with these things here. So what you're finding here is that you really have a couple of things that we should probably list here. And I think this is worth looking at. And what I mean by this is that I mean this type of thing. What you're finding here is that you have this, how do you spell macro? I think there's a C. I don't even care. I should have just put goddamn quotes on the damn thing. Okay, so if I'm looking at this thing microscopically, we're really looking at the world in terms of, EM waves. What do I mean by EM waves? What you found here in these EM waves here is that it describes extremely well interference and diffraction. There was no way a particle model could describe what was going on. But with the black body radiation, with the photoelectric effect, what you find is that it had trouble with black body radiation and photoelectric effect. Okay, it had trouble with it. Now, when you start to look at this thing microscopically, and in this world, it's Einstein that really comes up with the so-called photons. And what we know about photons, of course, is that it's what? It's localized energy. And what we're seeing here, what emerges here, in this case, is that it can explain black body radiation. And remember, that's the infinite energy problem and the photoelectric effect. Now, I want to say that at this time in the world, what ended up happening is that Einstein was literally alone. There might have been 10 people in the world that may have believed in the photon. Einstein fought tooth and nail for the photon. And in fact, he became quite stubborn at one point. I think it was in 1908. He went back and revisited the black body radiation problem, and he did a particle calculation with massless particles, and he re-derived the black body radiation curve with massless particles in a box. And Einstein then sort of like bared down, and he says the photon is real, but people you could read the literature back then, they would just say, that guy's really brilliant as long as you don't listen to his photon model. They literally were patronizing him because of the photon model. And some people said that the reason why he even went on to develop the general theory of relativity, he was so frustrated with the photon that nobody would believe him. So he needed a respite in order to handle, the photon later on. And then he found out he didn't like the photon either, like most of the people. And so what we find here is that if you look at quantum mechanics books, what you're finding here is that they're setting up a dichotomy. And you can see the dichotomy, right? What you're finding here is that what emerges is a dichotomy. And when I think about a dichotomy, remember what that means. It's two contradictory opinions. Right? It's two contradictory opinions. And what they keep saying here is light, a wave, or a particle. And you're going to find that as you look at quantum mechanics, this is something that pops up again and again and again. And in fact, they even call this a wave particle duality here. And what I'm trying to say here is that textbooks try to pin you into a point that just says, well, is it a wave or is it a particle? It's neither. It's a photon. Don't put yourself into a corner where you're driving into a dead-end alley and you're going to run into trouble. Textbooks try to make you go like, wow, is it really a wave? It's both. And it's neither. You got to understand that it's its own thing. Don't let people do that to you, especially when you start to get into these quantum mechanical things. So what I want to do here is that I want to do the following thing. I want to go in and clearly the photoelectric effect states that the photon is a particle-like thing. So from the photoelectric effect, this clearly says that it must be a localized energy packet. And here's the thing here. Anytime you say the word localized, right? Localized, it's not enough to say energy, right? It's not enough just say energy, but you must include momentum, right? A car is a localized thing. So as a car is moving, we know that it has energy and we know it has momentum. If a billiard ball is moving, we know it has energy, we know that it has momentum. Anything that's localized has to be that case. And here's where now, so if you start to put this together, we take Planck and Einstein together, and look what emerges here. If I have an energy of a photon, then we know from the previous chapter that the energy of a massless particles must be Pc. But at the same time, if we look at Einstein via Planck, right? Planck really kind of set that thing up. You could see here that the momentum of a photon then should be related to this quantity, which is of course this guy now. So that means if I have a massless particle, it could have momentum that's related to the wavelength, right? So a massless particle has a wave-like character. And this is a very, 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 very deep statement, okay? A very deep statement. And I don't want to expand too much because I don't want to get off topic, but this statement right here is huge. And this is also known as a de Broglie wave, which we'll talk about later. But this is for a massless particle. But it turns out that this characteristic is true for any quantum particle. So what I want to do here is that I want to go in and I want to keep talking about what we know. So the thing about it here is that, and I want to remind you here is that remember, electrons do not absorb photons. I don't give a shit what online says. Okay? I don't give a shit what online says. Okay? So what you want to do here is that when you do this, what you're finding here is that if I have this localized, right? So this means here that if I have a localized packet, then it must collide, scatter like like billiard balls or cars, whatever you want to think about it. So that means here, what that means here is that with the photoelectric effect, what you ended up seeing here is that you're seeing what? In the photoelectric effect, you talked about atoms dealing with the light itself, but it never interacted with the single electron. So the photoelectric, so the black body and photoelectric effect dealt with atoms, not single electrons. And the question is why? They didn't have the technology. The technology couldn't get below atomic structure. So now, what you find here is that now, around the 1925, or let's say the 1920s, I think it was 1922. Now, 1920s technology could see electrons. And because it could see electrons, now photons can interact with electrons. So you could see why there's a progression. The only reason why they could start to interact with single electrons was because of technology here. When you have photons interacting with charged particles, it's known as Compton scattering. And in order to see something, you have to be comparable to the size of that thing. And what you're finding here is that, and the reason why this is here is sort of like this. So to see something, okay, wait. I'm doing a contradictory thing here. To see something classically, okay, to see something classically, the wavelength must be comparable to the size of the object. So if it's the size of the object, now look what I'm going to do here. Now I'm going to go back to quantum physics. I'm walking a knife's edge, because when you look at the energy, we just saw that that is the case. But look at this. If I reverse it, then this tells me here in the limit, as the energy gets large, the wavelength becomes very small. And because it's very small, then that means you can now see inside the atom at electrons. That's why they were able to see the electrons for the first time. And who was it? It was none other than Compton. Compton won his Nobel Prize, and there was no way that classical physics could explain what was going on. So here we go. So what do I want to do? What I want to show you here is that Compton scattering, it's known as the Compton effect, the Compton shift, or the Compton scattering is important because it demonstrates that light cannot be explained purely as a wave phenomenon. I would say that it's probably the second easiest way of doing this. Now, we have to be really, really careful here. Textbooks really miss this a lot because they don't want to get into the deepness of it. It turns out that you could explain high intensity light with Compton scattering, but you cannot explain low intensity light with Compton scattering. Remember how I said that the most important thing about the photoelectric effect, it was low intensity light ejecting electrons from a metal. The same thing happens with Compton scattering, that low intensity light shining off of electrons could not explain the data. So this experiment was not the nail in the coffin. The photoelectric effect was the nail in the coffin, but this solidified it without any doubt. And it tells us without any doubt why classical physics failed. So because it demonstrates it again points to that classical physics fails. It's really the end of classical physics. And if you really want to learn more about this thing, what you want to do here is that you want to go in and you want to look up what is known as Compton scattering. It's the classical theory of electromagnetic waves scattered off of a charged particle. And so let's talk about the experiment. So when I look at the experiment, the big technology was an X-ray tube. So what you find here is that you have an X-ray tube, okay? And an X-ray tube, very similar to a microwave in some sense, where what it does here, it essentially accelerates or stops charges very quickly. And as a consequence, it emits radiation in the forward direction. So if you think about sort of like the X-rays, the first X-ray machines were literally about stopping electrons very quickly. And then it produced the X-ray. So what you find here is that you take it, and then what they're going to shine it on is they're going to shine it on a graphite. So what you have here is that you have a graphite target. Now, I want to remind you that a graphite target is nothing but a piece of pure carbon, if you wanted to look at it that way. Or it's not pure, but it has very few impurities in it. So what you do here is you take a beam, you shine it onto this thing, just like the photoelectric effect, but now you're shooting X-rays. So then you shoot this guy, and what you then have here is that you have a series of slits. And what these slits do is that they collimate the beam. Okay, so what they do here is that they're called collimating slits. And what that means here is that if you have different wavelengths, if I could say that, what you'll see here is that you get some scattering off of the graphite that goes in multiple directions. And what this really does here is it gives you a pencil thin beam. So now you got a real thin pencil beam here. And so then this guy continues to go here, and then it hits a crystal. Okay, so when I think about this crystal here, I could imagine that this crystal looks something like, let's say, oops, wrong color. I have a crystal here. And what this crystal does here is it actually, by hitting this crystal together with what is called, so then if I look at this guy here, let me say this. And then it comes in, and now I have a detector here. And here's my detector. And the detector, what it does here is it's really an ionization chamber. That means once it starts interacting with this thing, you get a cast. Oh, no, I don't want to go into the details. Let's just leave it there. It just detects the X-rays. And so what you're seeing here is that this guy works as one unit. Okay, this is one unit. And what you'll find here is that this whole unit here now rotates in a circle. So you can rotate this any way you want here. And so this guy right here is a circular track. And one of the things that I think is interesting, which I did not set up, let me see if I could go get it here. What I want to do here is that I want to do this thing, and I want to just share with you a little bit. So if you were to kind of look at this, this is not the same kind of thing here. I'm going to really distort this thing. So one of the things here, this is if you look at this building right in here, at Stanford, this is called End Station A. And you can see that right here is the 2-mile Stanford Linear Accelerator. And then they have a switching yard, which would then send it into here. So the way they discovered that there was stuff inside a proton is that they increased the energy enormously, and they reduced the wavelength so small that they could now go inside the proton and see that there was constituents. By the way, very similar to how they saw electrons for the first time in Compton scattering. Now, this experiment is a different style of experiment because it uses Bragg diffraction. This uses a different thing. And so what happens here is that the beam comes into here, and inside of here is that there's not a crystal, but there's another way that deflects the beam. And then right here is the ionization chamber. So what you can do here is that, I don't know, can you see, this is pretty small here, but if you look right there, there's a railroad track. And the railroad track is it would just rotate back and forth on this railroad track. You know, I probably shouldn't say this, but there's something kind of disgusting. And it's this thing right here. If you look, That pink area is a massive concrete door. It's probably 5 feet thick, probably 40, 50 feet. And so they would open this concrete door. And it turns out that when I was a graduate student, since I was extremely poor, they would pay me, and another graduate student. So I wasn't the only one. I think there was like 3 or 4 of us. We would give tours of Slack. And what's really funny, well, I think it's funny. It's terrible, by the way. It's not, it really isn't funny, but hear the story. So what ends up happening is that this door, when it closes, moves at a snail's pace. Like it moves really, 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 really slow. And this thing is just tons and tons. And it's just moving really, really slowly. And one time, as they were going to start to do an experiment, they're closing the door and a bird tries to fly in. And right at the corner of this door, that's like 50 feet, that probably moves, an inch or 2 per second, smashes this bird in the corner. And it was there ever since I was there. So every time I give a tour, I go like, check out the bird in the corner. It got pasted by this damn door. Okay, I had to get that out of my mind so I could focus on what I needed to do here. So what you're finding here is that this type of experiment is exactly what ended up happening with these Compton experiments. So what you're going to see here is that you're going to see the following thing here. What you'll find is that the way it works is it works something like this here. So what you'll find here is that this is what they're doing. So the first thing that you're seeing here is that when Compton did the experiment, he had a wavelength of 0.0709 nanometers. So his X-ray tube produced that. So this number is important. The question is, why? The diameter of a hydrogen atom. Uh-oh, that's not spelled right. That's okay. Hydrogen atom is 0.10 nanometers. So look at that. The wavelength of the X-ray is going to be what? Less than the diameter of hydrogen. So that means that they're going to do what? They're going to see inside of a carbon atom. So when I look at a carbon atom, what do I see here? So a carbon atom, if you look at it, right, it has a positive nucleus, and carbon has 2 shells, right? It has 1, 2. And when you look at these things, it has electrons here, and then it has 6 electrons there. And what you're seeing here is that now, what you're finding here is that I have these inner electrons, and the inner electrons are more tightly bound. Why? They're closer to the nucleus, that's true, but the more important thing, which is a physics 4B thing, is that there's no charge screening. Charge screening is the reason why electrons become weakly bound. And then these guys here are less tightly bound. Okay, less tightly bound. So that's what you're going to see here. So what you're seeing here is that you get this here. So if I look at the graphite, remember, if I say graphite, I really mean carbon. So if I look at my graphite target, what you're seeing here is that if I look at copper, copper looks like this, let's say. And its structure is pretty rigid here. And what you're going to see here is that you're then going to send in waves that come in, right? We say light waves classically, but as they come in, what you're going to see here is that they're going to interact with these things here, right? So these are my X-rays. These are my, oops, not there. These are my carbon atoms. And what you're going to see here is that this is what ends up happening. Compton measured electron scattering from photons. And when he does this, here's what he measured. He measured the intensity versus the wavelength. So in the wavelength, what you're going to see here is he's going to get this here. He's going to have two peaks here. Going to have a peak here versus a second peak here. And so what you're going to find here is that if I truly have scattering, right? If I truly have scattering, you're going to see that this guy's going to be the incident photon, and this guy's going to be the scattered. So this is the scattered photon, and this is going to be the incident photon. And what he measures is he measures this wavelength difference. Okay, so Compton, the way he measures that is he looks at the wavelength shift. That's what his experiment does. And he does this for 4 angles. He only has 4 angles. So what you're going to see here, the wavelength shift, and he measures this for 4 angles. And these angles are very well known here. Of course, he picks simple angles, but now people have done all the angles. But I think 4 is all you need to do here. So what we want to do next, and the first part of this thing is going to be quite tricky because I got to explain what the first peak means versus the second peak. But I'm going to stop right here.